This is an audio recording for visually impaired students from the book Pardeep's Physical Chemistry, Volume 1 by Dr. S.C. Khetarpal. Chapter 3 Solid State. First heading 3.1 Solids and their classification. A solid is defined as that form of matter which possesses rigidity and hence possesses a definite shape and a definite volume. The solids are divided into two types, namely crystalline and amorphous. First, crystalline solids. A solid is said to be crystalline if the various ions, atoms, or molecules of which the solid is made up are arranged in a definite geometric pattern within the solid. All solid elements and compounds exist in this form. The crystalline solids are further classified into a number of types which have been discussed in section 3.3 along with example of each type. Second, amorphous solids. A solid is said to be amorphous if the constituent ions, atoms, or molecules of the substance are not arranged in any regular fashion, although it possesses rigidity, definite shape, and definite volume. Example, glass, pitch, rubber, polymers of high molecular mass, etc. In fact, the amorphous substances are not regarded as true solids. Rather, they are considered to be highly supercooled liquids of very high viscosity. Second heading 3.2 Points of difference between crystalline and amorphous solids. First, arrangement of particles. In a crystalline solid, the constituent particles are arranged in a definite geometric pattern, whereas in an amorphous solid, they are not arranged in any regular fashion. Second, melting point. The crystalline substance possess sharp melting points, whereas the amorphous substance melt gradually over a temperature range. Third, isotropy and anisotropy. In case of amorphous substances, properties like electrical conductivity, refractive index, thermal expansion, etc. are identical in all directions, just like in case of gases or liquids. This property is called isotropy, and the substance showing this property are called isotropic. On the other hand, in case of crystalline substances, the properties mentioned above have different values in different directions. This type of behavior is called anisotropy, and the substance exhibiting this type of behavior are called anisotropic. Thus, whereas amorphous substances are isotropic in nature, the crystalline substances are anisotropic. The anisotropy exhibited by crystalline substance is obviously due to the fact that in making measurements in different directions, different types of particles fall on the way as shown in figure, or the arrangement of particles is different. Exception: cubic crystals are isotropic because they have the same structure in all directions. Fourth, regular and irregular cut. A crystalline solid on being cut with a sharp-edged knife gives a clean cleavage, whereas an amorphous solid undergoes an irregular breaking as shown in figure. Fifth, cooling curves. When a molten crystalline solid is cooled and temperature is plotted against time, the cooling curve obtained has breaks at the point whereas solidification starts and where the solidification is complete. The heat evolved during solidification keeps the temperature constant. Cooling of a molten amorphous solid gives a smooth cooling curve without any break. The main points of difference between crystalline and amorphous solids may be summed up as follows. Table 3.1 Comparison of characteristics of crystalline and amorphous solids. Crystalline solids. First, the constituent particles are arranged in a regular fashion containing short range as well as long range order. Amorphous solid. The constituent particles are not arranged in any regular fashion, they may be at the most some short range order only. Second, crystalline solids. They have sharp melting points. Amorphous solids. They melt over a range of temperature. Third, crystalline solids. They are anisotropic, that is, properties like electrical conductivity, thermal expansion, etc. have different values in different directions. Amorphous solids. They are isotropic, that is, properties like electrical conductivity, thermal expansion, etc. have same value in different directions, just as in case of gases and liquids. Fourth, crystalline solids. They undergo a clean cleavage. Amorphous solid. They undergo an irregular cut. Fifth, crystalline solid. Cooling curves of molten solids have breaks. Amorphous solid. Cooling curves do not have breaks. Thus, to see that the given solid is crystalline in nature, it must exhibit the following characteristics. First, possess a definite geometry. Second, possess a sharp melting point. Third, exhibit an anisotropy. Fourth, should give a clean cleavage. Next heading 3.3 Classification of crystalline solids. Based upon the type of constituent particles occupying the lattice sites and hence the type of binding forces, the various crystalline solids are classified into the following different types. First, ionic crystals. In these crystals, the constituent particles occupying the lattice points are the positive and negative ions, example Na positive and Cl negative ions in case of NaCl crystal. These ions are held together by the strong electrostatic forces of attraction. Some of the important characteristics of these crystals are as follows. First, because of strong electrostatic forces of attraction existing among the ions, they have high melting and boiling points. Second, they are good conductors of electricity in the molten state or in the solution but not in the crystalline state where the ions are not free to move. Third, they are soluble in polar solvents but insoluble in non-polar solvents. Fourth, because of strong electrostatic forces of attraction, the ions are closely pegged and hence the ionic crystals are hard. However, they are brittle because the stability of the crystals depends upon preservation of their geometric pattern. Second is molecular crystals. The constituent particles occupying the lattice points in this case are the molecules. The intermolecular forces holding the molecules together in the crystal lattice are the weak van der Waals force. In case of polar molecules, example HCl, H2O, NH3, etc., these van der Waals forces are the dipole-dipole attraction as shown in figure A. In case of non-polar molecules, example H2, Cl2, CH4, etc., the van der Waals forces are the London dispersal forces. These forces are believed to arise due to momentary dipole produced as a result of distortion of the electron cloud of one molecule, which produce an induced dipole in the other molecule as shown in figure 3.4. B. These have already been discussed in Unit 2. The main characteristics of the molecular crystals are as follows. First, as the van der Waals forces are much weaker than the electrostatic forces existing in ionic crystals, the molecular crystals are soft and have low melting and boiling points. Second, they do not conduct electricity in the solid or liquid state or in solution as there are no ions present. Third, they are less soluble in water and more soluble in polar solvents. Polar molecule liquids act as solvent for ionic compounds. Fourth, as dipole-dipole attraction are stronger than London forces, therefore polar molecular crystals generally have higher melting points and boiling points than crystals of non-polar molecules of comparable molecular size and shape. Third, atomic or network or covalent crystals. In these crystals, the lattice points are occupied by atoms which are linked together by a network of covalent bonds to form a giant molecule. One of the most common examples of the crystals of this type is that of diamond, in which the carbon atoms are linked together by covalent bonds to give a three-dimensional structure as shown in figure. Substances of this type have high melting points, high boiling points, low volatility, and are extremely hard because of the large number of covalent bonds that have to be broken to destroy the crystal structure. Further, they are non-conductors of electricity. Fourth, metallic crystals. These crystals consist of positively charged metal ion kernels occupying the lattice points, which are held together by the metallic bond. The metallic bond arises due to the presence of mobile electrons as the ionization energy of metals is low. These mobile electrons undergo simultaneous attraction by a number of positive ions and hence the ions are held together. Unlike ionic crystals, the positions of the positive ions can be altered without destroying the crystal because of the uniform charge distribution provided by the freely moving electrons. Thus, metallic crystals can be easily performed. That is why the metallic are malleable and ductile. The other properties of metals like luster, thermal, and electrical conductivity can be explained on the basis of the free-moving electrons. Further, as the positive ions are closely pegged in the crystal lattice, most of the metals possess high melting point and high density. It may be noted that melting bond differs from a covalent bond in the following two aspects. First, covalent bond is directional, whereas a metallic bond is non-directional. Second, metallic bond is weaker than covalent bond. To sum up, the various type of crystals, solids, their constituent particles occupying the lattice points, the type of attractive forces, their properties, and some examples are given in Table 3.2. Table 3.2. Classification of crystalline solid into different types. Crystal type: ionic, molecular, covalent, and metallic. Now let's discuss this. Constituent particles in ionic: positive and negative ions arranged in a definite order. Main binding forces: strong electrostatic forces of attraction. Properties: brittle, high melting point, good conductors in the aqueous solution or fused state, high heats of fusion. Examples: salts like NaCl, KNO3, LiF, BSO4, etc. Second, molecular crystal. Constituent particles, small molecules, mean binding forces, van der Waals forces. Properties: soft, low, melting point volatile, electrical insulators, poor thermal conductors, low heats of fusion. Examples: solid CO2 and CH4, wax, iodine, ice, sulfur. Third, covalent crystals. Constituent particles. Atoms chemically bound together in the form of a network. Main binding forces, covalent bond forces. Properties: very hard, high melting point, poor conductors of heat and electricity, high heats of fusion. Examples: diamond, silicon, quartz. Crystal type fourth is metallic. In this, constituent particles are positive ions and mobile electrons. Main binding forces are electrical attraction, metallic bond. And the properties: very soft to very hard, low to high melting point, conductors of electricity and heat, metallic luster, malleable and ductile, moderate heats of fusion. Examples: all metals and some alloys. The branch of science which deals with the study of geometry, properties, and structure of crystals and crystalline substances is known as crystallography. The study is based upon three fundamental laws. These are: first, the law of constancy of interfacial angles; second, the law of rationality of indices; third, the law of symmetry. Each of these laws will be discussed in the subsequent sections of this chapter. Further, the study of crystal structure involves two important aspects. These are: first, the study of the external shape or geometry of the crystal, also sometimes called the crystal habit. Second, the study of internal structure of the crystal. Now we shall proceed to describe briefly the various terms and aspects related to laws used in the study of the external shape and the internal structure of crystals, and then we shall also describe briefly the methods used to investigate the internal structure of the crystals. Next, heading 3.4, some terms used in crystallography. First is face. The plane surfaces of a crystals are called the faces of the crystal. Edge. The line along which the two adjacent faces of a crystal intersect is called the edge. Foam. A set of similar faces of a crystal is called a foam. The faces of any given foam make characteristic angle with each other and with other faces. Zone. Because of the regular shapes of a crystal, faces are found to occur in sets which meet in parallel edges or would meet in parallel edges if the planes of the faces are extended. Such a set of faces is known as zone. Crystal habit. The external shape of the crystal is called crystal habit. Interfacial angles. The angles between the adjacent faces of a crystal are called interfacial angles. Next, heading 3.5, Steno's law of constancy of interfacial angles. The crystals of a substance are obtained by cooling the liquid or the melt or the solution of that substance. The size of the crystals depends upon the rate of cooling. If cooling is carried out slowly, crystals of large size are obtained because these particles via ions, atoms or molecules get sufficient time to arrange themselves in proper position. Similarly, it is found that the shape of the crystals of a substance also depends upon the conditions under which the crystallization takes place, that is, in the absence or presence of any other substance, etc. For example, shapes of the crystals of a particular substance are shown in figure. However, in spite of the different sizes and shapes of the crystal of the same substance, the following regularity is observed. The angles between the corresponding faces, called the interfacial angles of the crystals of a particular substance, are always the same independent of the shape and size of the crystal. This is called the law of constancy of interfacial angles. The instrument used for the measurement of interfacial angles is called a goniometer. A very simple and common form of a goniometer is a contact goniometer. It has two flat arms pivoted together on the center of the straight portion of a semicircular scale, usually called D, as shown in figure 3.8. At the axis of their rotation, the two arms can be clamped at the desired angle with the help of a screw. Thus, the two arms are similar to that of a pair of scissors. The crystal is placed between the two arms such that its adjoining forces are touching the arms. The arms are then clamped and the angle between the arms is read from the scale. The above technique is useful only when the crystals are large in size with the clear-cut faces. However, for more precise work and for small crystals, an optical instrument called reflecting goniometer is used, or the best is an X-ray goniometer. Further, it is found that the form or shape or habit of the crystals of a substance also depends upon the conditions under which the crystallization take place, that is, in the presence or absence of any other substance, etc. For example, sodium chloride grows as cubes from water solution but as octahedral from 15% aqueous urea solution. A large variety of shapes of the crystalline substance have been observed. One is therefore tempted to classify the variety of shapes on some basis. Such classification is based upon the symmetries exhibited by the crystals and their internal structure. In next section, we shall therefore discuss the elements of symmetry possessed by crystals and molecules. Next heading 3.6, Elements of symmetry. The crystals of the various substances possessed the following different types of symmetries. First, center of symmetry. It is defined as an imaginary point within the crystal such that any line passing through this point intersects the opposite faces of the crystal at equal distances. The center of symmetry is called the center of inversion because if the crystal or the molecule is inverted through the center of symmetry, it gives results equivalent to the original and hence indistinguishable from the original one. For example, the center of inversion of a few molecules are given below, represented by solid dots. Second, plane of symmetry. It is defined as an imaginary plane passing through the crystal such that it divides the crystal into two parts in such a way that one part is the mirror image of the other. The planes of symmetry are therefore also called mirror planes. Third, rotation axis of symmetry. The rotation axis of symmetry, or simply called the axis of symmetry, is defined as the imaginary line passing through the crystal such that when the crystal is rotated about this line, exactly similar appearance occurs more than once in one complete revolution, that is in a rotation through 360 degrees. If similar appearance occurs twice in one complete revolution, that is after every 180 degree, the axis is called two-fold axis of symmetry or a dyad axis. Similarly, the other possibilities found for similar appearance in one complete revolution are thrice, 4 times or 6 times, that is after revolution through 120 degree, 90 degree or 60 degree. The corresponding axes are called threefold, triad, fourfold, tetrad and sixfold hexad axis of symmetry. The above type of rotation, which leads to equivalent configurations which are congruent as well, is called proper rotation, and the axis is called proper rotation axis. Further, it may be pointed out that we have only twofold, threefold, fourfold and sixfold axis of rotation, and we do not have fivefold, sevenfold, eightfold or higher fold axis of rotation, as will be explained later in section 3.13. Fourth, rotation reflection axis of symmetry. When the rotation of a molecule or a crystal about an n-fold axis of proper rotation is followed by reflection through a plane perpendicular to the axis is called an n-fold rotation reflection axis. The new configuration obtained is not congruent but is enantiomorphous. For example, rotation followed by the reflection of an asymmetric object like the numerical 7 is shown in figure. Fifth, rotation inversion axis of symmetry. When the rotation of a molecule or a crystal is followed by inversion through the center of symmetry, the axis is called an n-fold rotation inversion axis. The term equivalent should not be confused with the term identical. The former means that the new configuration is indistinguishable from the original one but is not necessarily identical with it. The equivalent configurations are further of two types. First, those equivalent configurations which are superimposable, these are called congruent configuration. Second, those equivalent configurations which are not superimposable, these are called enantiomorphous. Example, left hand and right hand. In inversion, since the relative position of the atoms change, the new configuration obtained is not superimposable and hence is enantiomorphous. An identical configuration is called obtained when the object is rotated through 360 degree. The new configuration obtained is not congruent but is enantiomorphous as in the above case. For example, rotation followed by inversion through the center of inversion of the numeral 7 is represented in figure. Corresponding to each proper n-fold axis, there is a rotation reflection axis represented as n-fold axis and a rotation inversion axis represented as n-fold axis. The above two types of rotation via rotation reflection and rotation inversion, which give enantiomorphous configurations, are called improper rotation, and the axes are called improper rotation axis. The various types of symmetries as discussed above are collectively called elements of symmetry, and the operations involved like rotation, reflection, inversion, etc. are called symmetric operations. Further, it may be mentioned that whereas a crystal may have many planes of symmetry, many axes of symmetry, but it can never have more than one center of symmetry. In some cases, there may be no center of symmetry at all because of the different development of the opposite faces during crystallization. Next, heading 3.7, Law of Symmetry. The crystals of a particular substance always possess the same elements of symmetry. This is called law of symmetry. For example, a cubic crystal always possesses the following 23 different elements of symmetry. A. Rectangular planes of symmetry 3. B. Diagonal planes of symmetry 6. C. Fourfold axis of symmetry 3. D. Threefold axis of symmetry 4. E. Two-fold axis of symmetry 6. F. Center of symmetry located at the center of gravity of the cube 1. An example of each type of symmetry possessed by a cube is shown in figure. Crystallographic, next heading 3.8, crystallographic axis and axial ratios. As already mentioned, a crystal has a regular arrangement of its constituent particles. The points occupied The points occupied by these particles within the crystal are called the lattice points. Any plane passing through a large number of lattice points is called the crystal plane. A very large number of sets of parallel planes exist within the crystal. Some such sets of parallel planes present within cubic crystal are shown in figure. The plane surface of a crystal are called the faces of the crystal. In order to describe the relative difference and the orientation of the faces and also the planes present within the crystal, three suitable axes are chosen which meet at the point say O. These axes can be selected in a number of ways depending upon the symmetries of the crystal. However, the best choice is usually the lines coinciding with or parallel to the edges between the principal faces. For example, in a cubic crystal, the best choice of the axis is the three lines mutually at right angles to each other. The three or four lines thus selected meeting at a point are called crystallographic axes. Now a suitable plane called the standard or unit plane is selected which cuts all the crystallographic axes. For example, suppose the three axes are represented by OX, OY and OZ and the unit X plane cuts these axes at A, B and C respectively, making the intercepts O is equal to A, OB is equal to B, OC is equal to C. The ratio A ratio B ratio C is called the axial ratio. Thus, the axial ratio may be defined as the ratio of intercepts made by the unit plane on the crystallographic axis. It is important to note that the actual lengths of the intercepts A, B, C depends upon position of the origin O, but their ratio is constant. It is therefore the ratio which is significant in describing the shape of a crystal. Further, it is convention to write B as unity. Example, for copper sulfate crystals, the axial ratio A is A ratio B ratio C is equal to 0.575 ratio 1 ratio 0.5575. The angles between the axes opposite to the intercepts A, B and C are represented by alpha, beta and gamma respectively. These angles are the same as the interfacial angles if the axes chosen are the lines coinciding with or parallel to the edges of the principal faces of the crystal. These angles together with the axial ratios are called the elements of the crystal. Howe's law of rational indices. If the intercepts of any other plane or face of the crystal on the three axes are measured, the following generalization is observed, which is called law of rational indices, put forward by R.J. Hoy in 1783. The intercepts made by any plane or face of the crystal on the crystallographic axis are either first same as those of the unit plane, or second simple whole number multiples of those of the unit plane, or third one or two intercepts may be infinity if the plane or the face is parallel to one or the two axes, that is, the plane or the face does not cut one or the two axes. For example, in figure, the intercepts made by the faces L, M, N are 2a, 2b, and 3c, which are simple whole number multiples of those of the unit plane. Again, consider the case of cube. Suppose the origin of the crystallographic axis lies at the center of symmetry and the axes OX, OY, OZ are parallel to the edges are shown in figure. Suppose the axis OX cuts the face ABCD at the point L. Similarly, suppose the axis OY and OZ cut the faces at M and N as shown in the figure. If LMN is taken as the unit plane, the intercepts made by the unit plane on the three axes are OL, OM, and ON. The face ABCD cuts the axis at L, that is, makes the simple same intercept as that made by the unit plane, but it does not cut the y-axis and z-axis at all because these two axes are parallel to this face. In other words, the intercepts made by the face A, B, C, D on the y-axis and z-axis are infinity. In general, if a face PQR makes intercepts P, Q, and R on the three axes and the intercepts made by the unit plane are A, B, C, then we have P is equal to NA, Q is equal to N dash B, and R is equal to N dash dash C, where N and N dash, where N double dash are simple whole numbers or sum out of these may be infinity. Next, heading 3.10, identification or dis, de- des- designation of crystal planes and faces. First, in terms of various indices, if a face makes intercepts NA, N dash B, and double dash C on the crystallographic axis, the face may be represented by N dash N double dash. The number N dash N double dash thus used to represent a face are called various indices. However, this method of representing a face is out of use. Second, in terms of Miller indices, it is more common to take the reciprocals of the number N dash, N double dash, and then multiply them by the smallest number, that is LCM of denominators, so as to express all the reciprocals as integers. The integers thus obtained are called Miller indices, proposed by W.H. Miller in 1839. Thus expressed as integers, or the Miller indices may be defined as the integers which give the ratio of the intercepts of the unit plane to those of the given plane or face, that is, the ratio A by NA, ratio B by N dash B, ratio C by N double dash, expressed as integers. Obviously, the Miller indices of given plane or face are inversely proportional to the intercepts of that plane or face on the crystallographic axis. Examples: in figure, the intercepts made by face LMN are 2A, 2B, 3C. The Weiss indices are 2, 2, 3. The reciprocals of the coefficients of A, B, C are 1 by 2, 1 by 2, 1 by 3. LCM of 2, 2, 3 is equal to 6. Multiplying the reciprocals by 6, we have 3, 3, 2. These are the Miller indices of the face LMN in figure. This face is represented as 3, 3, 2. Second, the intercepts made by the unit planes are A, B, C. The coefficients of these intercepts are 1, 1, 1. Hence, the unit plane is always represented as 1, 1, 1. Third, if some face does not cut some axis at all, the intercept on this axis is taken as infinity, as already explained in section 3.9. For example, suppose a face makes intercepts 2a and 3b on the x-axis and y-axis respectively and does not cut the z-axis at all, the intercepts will be 2a, 3b, and infinity or infinity c. The reciprocals of the coefficients are 1 by 2, 1 by 3, 0. LCM of 2, 3 is equal to 6. Multiplying by 6, the Miller indices will be 3, 2, 0. That is, the face will be represented as 3, 2, 0. Similarly, if a face makes intercepts a on the x-axis and does not cut y-axis and z-axis at all, its Miller indices will be 1, 0, 0. That is, it will be represented as 1, 0, 0. Fourth, if some intercepts made by a face is negative, that is, the face is cut by the axis when extended in the opposite direction, it is represented by putting a bar over it. For example, in figure, the intercept made by the face EFGH on the x-axis is minus a, and this face does not cut the y-axis and z-axis at all. Hence, this face is represented as 1 bar 0, 0. Fifth, Miller indices of the faces of a cube. referring to figure in which the origin of the crystallographic axis is the center of symmetry of the cube, and the following the method as explained in third and fourth above. The various faces of the cube in terms of Miller indices may be represented as 100, 010, 001, 1 bar 00, 01 bar 0 and 001 bar. All these faces are said to belong to the same form represented as curly bracket 100 curly bracket. Further, it is important to know that within the crystal there are a large number of planes passing through the lattice points in different directions. The directions and intercepts of these crystal planes are also designated in terms of Miller indices. Taking a simple case representing the lattice points in one plane of a crystal and taking the c-axis as perpendicular to the page, some sets of planes that are parallel to the c-axis, that is, which do not cut the c-axis, are shown in figure. In fact, there is an infinite number of such sets of planes. The faces and the crystal planes can be designated in a general way as follows. As usual, let ABC represented the lengths and axial direction of the unit cell as shown in figure. Let the plane ABC make intercepts OA, OB and OC on the axis. Then the ratio of the intercepts of those of lengths of the unit cell will be OA by A, OB by B and OC by C. The reciprocals of these lengths ratios will be A by OA, B by OB and C by OC. The set of x's is so selected that these ratios come out to be small integers, whole numbers. These small integers are represented by h, k and l. The Miller indices of the plane are then represented as hkl. Thus we may write h is equal to OA, A upon OA, K is equal to B upon OB, L is equal to C upon OC, or OA is equal to A upon H, OB is equal to L upon K, OC is equal to C upon L. For example, in the figure, the plane ABC make intercepts A 1 by 3A, 3 by 4B and 1 by 2C. The coefficients of the intercepts are 1 by 3, 3 by 4, 1 by 2. Their reciprocals are 3, 4 by 3, 2. To clear the fractions, multiply by 3, we get 9, 4, 6 as the Miller indices of the plane ABC. Distance of separation between HKL planes. Within the crystal, there are a large number of equally spaced parallel planes with the Miller indices HKL. One of these is supposed to pass through the origin. The perpendicular distance of the plane HKL from the origin is represented by DHKL, which will also be the interplanar distance of the adjacent parallel planes. This can be expressed in terms of the unit distance A, B and C and the Miller indices HK and L as follows. From figure, cos AOD is equal to D upon A by H. Cos BOD is equal to D upon B by K. Cos COD is equal to D upon C by L. Squaring and adding these equations, we get cos square AOD plus cos square BOD plus cos square COD is equal to D square H square by A square plus D square K square by B square plus D square L square by C square. If the axes chosen are orthogonal, that is alpha is equal to beta is equal to gamma is equal to 90 degree, as is the case of cubic, tetragonal and orthogonal crystal system, left hand side of the above equation is equal to unity. Hence, 1 upon d square hkl is equal to h square upon a square plus k square upon b square plus l square upon c square. Hence, 1 upon d hkl is equal to root over h square by a square plus k square by b square plus l square by c square. For a cubic lattice, a is equal to b is equal to c. So, 1 upon d hkl is equal to root h square plus k square plus l square by a, or d hkl is equal to a upon root h square plus k square plus l square. Alternatively, it may be derived in a simple manner as follows. Consider a two-dimensional lattice of orthogonal system in which A is not equal to B. The intercepts of the plane AB, the Miller indices HKL, on the a-axis, that is x-axis, and b-axis, that is y-axis, will be a upon h and b upon k respectively. Let OP be perpendicular on AB from the right-angled triangle OAB. AB is equal to root a by h square plus b by k whole square. From similar triangles OAP and OAB, d upon a by h is equal to b upon k by root a by h whole square plus b by k whole square, or d square bracket a by h whole square plus b by k whole square bracket close is equal to a by h whole square b by k whole square, or 1 by d square is equal to a by h whole square plus b by k whole square upon a by h whole square into b by k whole square is equal to 1 upon b by k whole square plus 1 upon a by h whole square is equal to h square by a square plus k square by b square. Extending to 3 dimensions, 1 upon d square hkl is equal to h square by a square plus k square by b square plus l square by c square, or 1 by d hkl is root over h square by a square k square by b square plus l square by c square. Calculation of distance of separation of nh, nk and nl planes from d hkl value of the lattice with orthogonal axes for nh, nk, nl planes. 1 upon d square nh, nk, nl is equal to nh square by a square plus nk square by b square plus nl square by c square is equal to n square into h square by a square plus k square by b square plus l square by c square is equal to n square into 1 upon d square nkl hkl. So d nh, nk, nl is equal to d hl hkl upon n. This implies that if the Miller indices are multiplied by a factor n, then the separation between the planes is reduced by that factor. For example, the distance between 2 to 0 planes is half than that of 1 1 0 planes as shown in figure. Note 1. The HKL planes divide are A into H equal parts, B into K equal parts and C into L equal parts. Second, smaller the value of H in HKL, the plane is more nearly parallel to A axis. The same is true for K and B axis and L and the C axis. Third, keeping in mind the reciprocal nature of Miller indices, a low value of H in HKL means an intercept at large distance on the a-axis or x-axis. A low value of k means a large intercept on the b-axis or y-axis, and so on. Fourth, when h is equal to 0, the plane intersects the a-axis at infinity so that 0 kl planes are parallel to the a-axis. Similarly, HOL planes are parallel to b-axis and HK0 planes are parallel to c-axis. Now there are some numerical problems based on Miller indices and interplanar distance. Next, heading 3.11 crystal system. In the various elements of symmetry, the distributed theoretically around a single point in space that is passing through the point, it is found that 32 different arrangements are possible. These different arrangements of the elements of symmetry about a single point are called crystal classes or crystallographic groups or point groups. Further, many points group have the same axial ratios and angles, that is 5 point groups out of 32 have alpha is equal to beta is equal to gamma is equal to 90 degree and a ratio b ratio c is equal to 1 ratio 1 ratio 1, that is a is equal to b is equal to c, and all these 5 corresponded to the cubic shape. In this way, the 32 points group have been regrouped into 7 types on the basis of axial ratios and angles. Since the external geometry of a crystal depends upon the axial ratio and angles, it implies that on the basis of the external geometry of the crystal, they are classified into 7 types, which are called crystallographic system. The names of these systems, along with their axial characteristics, maximum planes and axes of symmetry, the number of point groups belonging to each system, and the examples of each system are shown in table 3.3. The shapes of the various crystals are shown later in figure. Table 3.3 crystallographic systems and the related information. System. First, cubic system. Its axial characteristic: alpha is equal to beta is equal to gamma is equal to 90 degree. A is equal to B is equal to C. Maximum symmetry: planes is equal to 9, axis is equal to 13. Point groups 5. Examples: NaCl, KCl, alums, diamond. Second system, tetragonal. Its axial characteristics: A is equal to B is equal to gamma is equal to 90 degree. A is equal to B is not equal to C. Maximum symmetry: planes is equal to 5, axis is equal to 5. Point group 7. Examples: Sn, SnO2, TiO2. Third system, orthorhombic or rhombic. A alpha is equal to beta is equal to gamma is equal to 90 degree. A is not equal to B is not equal to C. 3 planes, 3 axes, 3 number of point groups. Examples: KNO3, K2SO4, BSO4, PbCO3, rhombic sulfur. Fourth, monoclinic. Alpha is equal to gamma is equal to 90 degree is not equal to beta. A is not equal to B not equal to C. 1 plane, 1 axis, 3 point groups. Example: Na2SO4.10H2O, CSO4.2H2O and monoclinic sulfur. Fifth, triclinic. Alpha is not equal to beta, is not equal to gamma, is not equal to 90 degree. A is not equal to B, not equal to C. Null plane, null axis. 2 point groups. Example, CuSO4.5H2O, K2Cr2O7. Sixth, bromohedral or trigonal. Alpha is equal to beta is equal to gamma is not equal to 90 degree. A is equal to B is equal to C. 7 planes, 7 axes and 5 point groups. Example, NaNO3, ICl ASSBBI. Seventh, hexagonal. Alpha is equal to beta is equal to gamma. Gamma is equal to, alpha is equal to beta is equal to 90 degree. Gamma is equal to 120 degree. A is equal to B is not equal to C. 7 planes, 7 axes, 7 point groups. Example, HGS, ICE, graphite, Mg, Zn, CD. Next heading 3.12, isomorphism and polymorphism. Certain crystalline substances which have similar chemical composition, example sodium phosphate and sodium arsenate, that is Na3PO4 and N3ASO4, are found to possess the same crystal shape. This phenomenon is known as isomorphism, Greek same shape, and the substances are said to be isomorphous. There are many substance elements or compounds which exist in more than one crystalline form, which are formed under different conditions of temperature and pressure. This phenomenon is known as polymorphism. For example, carbon exists in two crystalline forms which are graphite and diamond. Calcium carbonate exists in two crystalline forms called calcite and argonite. The polymorphism exhibited by the elements is commonly called allotropy. The temperature at which one crystalline form changes into another is called transition temperature. Next heading 3.13, space lattice and unit cell. So far we have been discussing only the external shape of the crystal. On studying the internal structure of the crystal, it is found that the particles, that is ions, atoms or molecules constituting the crystalline substance, are arranged in a regular fashion within the crystal in the three-dimensional space. For example, the arrangement of particles represented by black circles for a cubic crystal is shown in figure. The regular arrangement of points, that is ions, atoms or molecules constituting the crystal in the three-dimensional space within the crystal, is called the space lattice or crystal lattice. If a big sized crystal is broken more and more, ultimately a stage is reached when we get the smallest possible crystal. If it is broken further, it will break to give the constituent particles, that is ions, atoms or molecules. For example, if a big cubic crystal is broken, the smallest crystal obtained will be small cube as represented by thick lines in figure above. This small cube crystal has all the elements of symmetry as possessed by the big cubic crystal. Moreover, it is evident that the complete lattice has been obtained by the repetition of the smallest unit in different directions. The smallest portion of the complete space lattice, which has all the elements of symmetry and which, when repeated over and again in different direction, produces the complete space lattice, is called the unit cell. The situation may be compared with that of a thick wall made of bricks, where a brick similar to the unit cell and the wall to the complete space lattice. It may be pointed out that it is the regular arrangement of the points that constitutes the space lattice and not that of lines joining them. The lines have been drawn just to indicate the regular repetition more and not that of lines joining them. The lines have been drawn just to indicate the regular repetition more clearly and to describe the position of the points. Further, in order that the unit cell may be described completely, we should know the dimensions of the unit cell via A, B, C and angles alpha, beta, gamma between them as shown in figure. It may be recalled that in section 3.6 it was mentioned that we have only 2-fold, 3-fold, 4-fold and 5-fold axis of rotation, and we do not have 5-fold, 7-fold, 8-fold or higher fold axis rotation. This is obviously due to the fact that the most essential requirement of a lattice is that it should be built up by the repetition of unit cells, the faces of each unit cell touching the faces of the surrounding unit cells without leaving any gap in between. Such a close packing is impossible if an object has 2-fold, 3-fold, 4-fold or 6-fold axis of symmetry, but it is not possible in case an object has 5-fold, 7-fold, 8-fold or higher fold axis of symmetry. As an example, this is illustrated in figure for objects having 6-fold axis of symmetry and 5-fold axis of symmetry confining to two dimensions for sake of simplicity. The situation is similar to the fact that it is impossible to tile a floor with regular pentagons, heptagons, etc. without leaving gaps in the tiles. Next, heading 3.14, Brevius lattices. In the space lattice considered above, it was assumed that there are points only at the corners of the unit cell. The detailed study of the internal structure by Brevis 1848 has shown that the points particles may be present not only at the corners of unit cells but at the centers of the faces or within the body of the unit cells. This gives rise to 14 different types of lattices corresponding to the 7 crystallographic systems already described. These 14 types of lattices are called Brevis lattices. The description of these lattices is given in table 3.4 and the shapes are shown in figure 3.21 on next page. The terms of simple, face centered, end centered, and body centered imply as under. First, simple, when the points are present only at the corners of the unit cell. Second, face centered, when in addition to the points at the corners, there are points present at the center of each face of the unit cell. Third, and centered, when in addition to the point at the corners, there are points present in the center of the end faces of the unit cell. Fourth, body centered, when in addition to the points at the corners, there is one point present within the body each unit cell. The simple unit cell, that is when the points are present only at the corners of the unit cell, it is called primitive unit cell. The other types of unit cell are called non-primitive unit cells. These are some Brevis lattices corresponding to 7 crystallographic system. Now next is table 3.4, Brevis lattices corresponding to different crystal system. System cubic. Number of Brevis lattice 3. Description of the lattice simple, face centered, body centered. Second, tetragonal. Number of Brevis lattices 2. Description simple, body centered. Third, orthorhombic or rhombic. Number of Brevis lattices 4. Description simple, face centered, end centered, body centered. Fourth, monoclinic. Number of Brevis lattices 2. Description simple, end centered. Fifth, triclinic. Number of Brevis lattices 1. Description simple. Sixth, rhombohedral or trigonal. Number of Brevis lattices 1. Description simple. Seventh, hexagonal. Number of Brevis lattices 1. Description simple. The number of points per unit cell n is given by the expression n is equal to nc upon 8 plus nf upon 2 plus ni, where nc is equal to the number of points present on the corners of the unit cell, nf is equal to the number of points present on the faces of the unit cell, ni is equal to the number of the points present in the interior of the unit cell. This expression follows from the fact that each point present on the corner is shared by 8 unit cell, each point present on the face is shared by 2 unit cell, and the point present in the interior is shared by no other unit cell. For example, for any simple lattice, nc is equal to 8, nf is equal to 0, ni is equal to 0, so that n is equal to 8 upon 8 plus 0 is equal to 1. For a face-centered cubic lattice, nc is equal to 8 plus nf is equal to 6 and I is equal to 0, so that n is equal to 8 upon 8 plus 6 upon 2 plus 0 is equal to 4. For body centered orthorhombic lattice, nc is equal to 8 and f is equal to 0 and I is equal to 1, so that n is equal to 8 upon 8 plus 0 plus 1 is equal to 2. For end centered monoclinic lattice, nc is equal to 8 and f is equal to 2 and I is equal to 0, so that n is equal to 8 upon 8 plus 2 upon 2 plus 0 is equal to 2. Next heading 3.15, space groups. It has already been discussed in section 3.11 that theoretically there are 32 different ways of arranging the elements of symmetry about a point. These different arrangements are called point groups. However, in a complete space lattice, because of regular repetition of the pattern or in the three-dimensional space, two additional symmetry elements are called glide planes and screw axes become possible. The detailed discussion of these new elements of symmetry is beyond the scope of the present book. However, it is interesting to mention that because of these additional elements of symmetry, the number of arrangements possible for the elements of symmetry about a point of a space lattice becomes manifold. We are equal to 230. The 230 possible arrangements of the elements of symmetry about a lattice point are called space groups. The split of these space groups corresponding to the different crystal systems is given in table 3.5 on next page. Table 3.5. Distribution of space groups among crystal systems. Systems cubic. Number of space groups 36. Second tetragonal 68. Third orthorhombic 59. Fourth monoclinic 13. Fifth clinic triclinic 13. 2. Sixth trigonal or rhombohedral 30. Seventh hexagonal 22. To sum up, number of crystallographic systems 7, number of point groups 32, number of Braves lattice 14, number of space groups 230. Next heading 3.16. X-rays diffraction by crystals, study of the internal structure. The external shape of a crystal could be seen with the help of an optical microscope. On the basis, the crystals were classified into 7 systems as already discussed. However, the internal structure, that is the exact position of each atom within the unit cell, could not be studied until the discovery of X-ray by Roentgen in 1895. Using X-rays, the different studies that have been carried out to understand the internal structure of crystals are briefly described below. Next, 3.161. Louis method. Max von Louis in 1912 made a valuable suggestion that if a crystal consists of a large number of atoms or ions arranged in an ordered manner, and the atomic planes in the crystals were separated by distance which are of nearly the same magnitude as the wavelength of the X-ray, then if these X-rays are allowed to strike the crystal, the rays will penetrate into the crystal and will be scattered by the electrons of the atoms or the ions of the crystals. The rays reflected from different layers of atoms due to wave nature will then undergo interference, constructive and destructive, to produce a diffraction pattern, just as it happens in case of light passing through a grating containing a large number of closely spaced lines. In other words, crystals should act as three-dimensional grating for X-rays. These ideas of von Louis were put to experimental test and found to be true. In the Louis method, continuous spectrum of X-ray called white radiation having a wide range of wavelengths is used. Example from tungsten target. The purpose to do so it is that at least some of the radiation would have the proper wavelength to undergo interference. The method used in shown figure A, the line Louis diagram obtained for NaCl in shown in figure. Such diagrams confirm the definite arrangement of the atoms in a crystal. However, their interpretation to know the exact arrangement of atoms within the crystal is difficult. A much simple method has been put forward by W.H. Braggs as discussed below. X-rays are scattered by electrons. In neutron diffraction, neutrons are scattered by the nuclei of the atoms or ions of the crystals. Next heading 3.16.2. Bragg's method. Principle. The Bragg's method for study of the internal structure of crystals is based upon Bragg's equation put forward by W. L. Bragg in 1919, which may be derived as follows. A crystal may be considered to be made up of a number of parallel equidistant atomic planes as represented by the lines x x dash, y y dash, z z dash, etc. in figure. Suppose a beam of X-ray is incident on the crystal at angle theta. A part of the beam, example the ray AB, is reflected at the point B along the path BC. On the other hand, some rays like D, GH, etc. penetrate into the crystal and are reflected by the atoms present in the atomic plane Y, Y dash, Z, Z dash, etc. as shown in figure. Evidently, as compared to the ray AB, a ray like DE has to travel a longer distance equal to JEK in order to emerge out of the crystal, where BJ and BK are perpendiculars drawn on the lines DE and EF respectively. The reflected beams like BC, EF, etc. then undergo interference. The reflected beams like BC, EF, etc. then undergo interference with each other if these reflected rays are in phase, that is, in the reflected rays crest fall over the crest and troughs over the troughs, they reinforce into each other hand and the intensity of the reflected rays is maximum. On the other hand, if the reflected rays are out of phase, that is, crests fall over the troughs, the intensity of the reflected beam is very low. If a photographic plate is placed to receive the reflected rays, diffraction pattern is obtained. It is obvious that in order that the reflected rays BC and EF may be in phase, the extra distance JEK traveled by the ray DEF should be an integral multiple of the wavelength lambda of the X-rays, that is distance is equal to JEK is equal to n lambda, where n is an integer, that is 1, 2, 3, 4, etc. If d is the distance between the successive atomic planes, it is obvious from figure that JE is equal to EK is equal to d sine theta, so that JEK is equal to 2d sine theta. Putting this value in equation, we get 2d sine theta is equal to n lambda. This equation is called Bragg's equation. It gives us the condition under which the reflected beam will have maximum intensity using monochromatic X-ray. Lambda is constant also for a particular crystal. When a particular face is facing the X-ray, D is constant, hence n will be integer only for certain values of the angle theta, thus gradually decreasing the value of theta. A number of positions are observed corresponding to n is equal to 1, 2, 3, 4, etc., where the reflected beam will have maximum intensity. For other values of theta lying in between, the reflected beam will have intensity less than the maximum. Thus a diffraction pattern will be obtained in which the various maxima correspond to n is equal to 1, 2, 3, etc. These are respectively called diffraction maxima of the first order, second order, third order, etc. Measuring the angle theta at which the first maximum occurs, that is first maximum intensity, is observed, so that n is equal to I, and knowing the wavelength lambda of the x-axis X-rays used, the value of d can be calculated using equation 3. Apparatus. The apparatus used by Bragg for studying the internal structure of crystal, that is for a measurement of the intensity of the reflected beam corresponding to different values of the angle theta, is called Bragg's X-ray spectrometer and is shown in figure. X-ray generalized in the X-ray tube A. These are made monochromatic by passing through the absorbing screens B. Then they are passed through the leads slits L to obtain a fine beam. This beam is then allowed to fall on some particular face of the single large crystal C, which is mounted on a turntable T. The turntable can be moved over a circular scale as the reflected beam is passed into an ionization chamber D, which is connected to an electrometer E. The ionization chamber can also be moved on the circular scale as independent of the turntable T. The chamber contains some easily ionizable gas such as sulfur dioxide. Greater is the intensity of the reflected beam, greater is the ionization produced in the gas, the larger is the reading of an electrometer. When the crystal face is rotated, by rotating the turntable, the direction of reflected beam changes to receive the reflected beam into the ionization chamber. Every time the ionization chamber is rotated through the double the angle through which the crystal face is rotated. From these plots, the angles corresponding to the first, second, third maxima, etc., are noted and the value of d calculated using Bragg's equation, where 2d sine theta is equal to n lambda. Evidence in favor of Bragg's equation. For sodium chloride crystals, for the phase 100, the first, second, third maxima occur at angle 5.9 degree, 11.85 degree, and 18.15 degrees using X-rays produced from palladium target. The signs of these angles are 0.103, 0.205, and 0.312, which are very nearly in the ratio 1:2:3. This proves that the first, second, and third maxima occur on n is equal to 1, 2, 3 respectively. Hence, the correctness of the Bragg's equation is confirmed. The small hump on the left of each maxima is due to the beta radiation accompanying the X-rays used. Calculation for Bragg's equation. According to Bragg's equation, 2d sine theta is equal to n lambda, or d is equal to n lambda 2 sine theta for a particular phase HKL of the crystal, knowing the angle theta at which the first order diffraction maxima is obtained, so that n is equal to 1, and also knowing the wavelength of the X-rays is used. The interplanar spacing d can be calculated further. For a cubic system, the values of dHKL is given by dHKL is equal to a upon root h square plus k square plus l square. Knowing the value of dHKL calculated from equation above, the length a of the edge of the cube unit cell can be calculated. Alternatively, knowing the interplanar spacing dHKL, which can be calculated from equation 3, if the edge of the unit cell is known, And knowing the value of theta at which first order diffraction maxima is obtained, equation 1 can be used to calculate wavelength lambda of the X-rays used. Also knowing lambda and d using equation 1, theta can be calculated for a given value of n. X-rays are the length of a of the edge of cubic unit cell as obtained from Bragg's X-ray diffraction studies using equations 2nd and 3rd can be checked by calculation from an alternative method based on the knowledge of the density of the crystal and the type of lattice of the unit cell. Taking the example of NaCl crystal, which is face-centered cubic, it has 4 Na positive and 4 Cl negative ions per unit cell. Explained later in section 3.18, that is, it has 4 NaCl units per unit cell. Mass of unit cell is equal to mass of 4 NaCl units. It is equal to 4 into mass of 1 NaCl unit is equal to 4 into m upon Na, where m is equal to molar mass of NaCl is equal to 58.5 gram per mole and NO is equal to Avogadro's number if rho is equal to the density of NaCl crystal, which is equal to 2.165 gram per centimeter cube. Volume of unit cell is equal to 4 into m upon rho into NO. So edge of the unit cell is equal to 4 m upon rho NO whole power 1 upon 3. The value of the edge A thus determined is found to agree very well with the calculated from Bragg's method. This further gives support to Bragg's X-ray diffraction method. The method also tends support to the structure of NaCl as conceived and used in the calculation above. Now there are some problems based on Bragg's equation. The interplanar distance of the three types of cubic lattices can be calculated using the formula dHKL is equal to A upon h square root h square plus k square plus l square. These values in each cases are given below its figure. The ratios of the interplanar distances for each type of lattice will be as follows. Simple cubic d100 ratio d110 ratio d111 is equal to a ratio a upon root 2 ratio a upon root 3 is equal to 1 ratio 0.707 ratio 1.577. Face centered cubic d200 ratio d220 ratio d101 d111 is equal to a upon 2 ratio a upon 2 root 2 ratio a upon root 3 is equal to 1 ratio 0.707 ratio 1.154. Body centered cubic d200 ratio d110 ratio d222 is equal to a upon 2 ratio a upon root 2 ratio a upon 2 root 3 is equal to 1 ratio 0.414 ratio 1.577. To see to which type of cubic lattice the crystal belongs, the reflection from the different planes are studied and the angles are determined at which these reflections take place. The interplanar distance for each set of planes is calculated using Bragg's equation, where d is equal to n lambda upon d 2 sin theta. The ratio of the interplanar distance of the three planes is then calculated and compared with theoretically calculated ratios for the different types of cubic lattice given above. Determination of structure of NaCl, KCl and CaCl from the external geometry as found using optical microscope. All three, that is NaCl, KCl, CaCl, have been found to belong to cubic system. In case NaCl crystal, the first order reflections from three faces of its crystal are found to occur at 5.9 degree, 8.4 degree and 5.2 degrees respectively. Applying Bragg's equation, that is 2d sin theta is equal to n lambda or d is equal to n lambda upon 2 sin theta, it is evident that the ratio of three interplanar spacings will be in the ratio of 1 by sin theta values as n and lambda are constant for the given experiments. Thus, they will be in the ratio 1 upon sine 5.9 degree ratio 1 upon sine 8.4 degree ratio 1 upon sine 5.2 degree is equal to 1 upon 0.103 ratio 1 upon 0.146 ratio 1 upon 0.091 is equal to 9.71 ratio 6.65 ratio 10.99 is equal to 1 ratio 0.705 ratio 1.132. As the ratio is close to that of face-centered cubic, hence the given crystal NaCl has a face-centered cubic lattice. Proceeding exactly in the same way as above, it is found that KCl also has face-centered cubic structure, whereas CaCl has body-centered cubic structure. Now next is example for the same and some problems for practice. The powder method. This is simplest method for studying the X-ray diffraction by crystals. It was developed by Digay and Skinner in 1916 and independently by Hull in 1917. In the Bragg's method, a single large crystal is required, which may be sometimes difficult to obtain, and moreover it has to be rotated about a suitable axis, whereas in this method the simple sample is taken in powdered form in a small thin walled glass tube, capillary tube, and no rotation is required. Of course, the tube is rotated to ensure that the crystallities, small crystals is the powder, are randomly oriented. A beam of monochromatic X-rays focused on the sample and a circular photographic film is placed around it as shown in figure. Since the powder, the crystal planes of different small crystals are oriented at all possible angles to the beam. There will be always some crystals which will have the proper orientation to produce diffraction maxima from all the planes simultaneously. In principle, each set of HKL planes will give rise to diffraction cone originating from the powder. Thus, a large number of concentric cones will be produced due to the reflection from different sets of planes and satisfying Bragg's law. Each cone will meet the photographic film of 2 points, producing two lines or areas at equal distance from the bright center spot produced due to the diffracted beam. Thus, a large number of lines or arcs will be obtained on the photographic film, each pair of lines being equidistant on the right and left from the center spot. Further, if the incident angle is theta, the reflected beam make an angle 2 theta with the direction of the incident beam as shown in figure. An approximate idea of the general diffraction pattern of the powder may be as shown as given in figure. After getting the X-ray diffraction pattern of the powder, the next step is the indexing of lines, that is, assigning Miller indices to the planes responsible for producing these lines. For the purpose of distance, X-ray X of each line from the central spot is measured usually by taking half of the distance between the two lines of the same cone on either side of the center. If the radius of the film is r, the circumference 2 pi r corresponds to a scattering angle of 360 degree. This implies that 2 theta upon 360 degree is equal to x upon 2 pi r. Thus, theta can be calculated knowing theta. The interplanar spacing can be calculating using Bragg's equation via 2d sine theta is equal to n lambda. The diffraction pattern obtained by powder method are characteristics of the solid substances, that is, the position of the lines on the photograph depend upon the spacing between the crystal planes and hence on the type of crystal. For this reason, this method is quite often used for qualitative as well as quantitative analysis, that is, to identify and estimate pure substance and mixtures. Moreover, this method is much easier than the single crystal method. Next, heading 3.17, X-rays diffraction patterns of cubic lattice. Cubic system is the simplest of all the systems because all length of the unit cell are equal and each angle is equal to 90 degree for any set of planes with Miller indices HKL. The interplanar distance can be calculated using the expression DHKL is equal to A upon root h square plus k square plus l square. Also, according to Bragg's equation for glancing reflection, that is the first order diffraction, 2DHKL sin theta is equal to lambda, or sin theta is equal to lambda upon 2DHKL. Substituting the value of DHKL from equation 1, we get sin theta is equal to lambda upon 2 into root h square plus k square plus l square upon a, or sin square theta is equal to lambda square upon 4a square into h square plus k square plus l square. For a given cubic system and for the particular X-rays used, a and lambda are constant, hence lambda square upon 4a square is constant. Putting these constants equal to a, equation 4 becomes sin square theta is equal to h square plus k square plus l square into a. Substituting the values of the indices HKL for the planes present in the three types of cubic lattices, the value of theta in terms of sin square theta can be calculated, which predict the lines that would be obtained on the photographic film. This is explained below for each of the three cubic lattices. First, primitive cubic lattice. Using equation and integral values for the indices HK and L, DHKL may have values given in table 3.6 below. Note that a upon root 7 is missing because 7 cannot be obtained from h square plus k square plus l square when K and L are integers, the corresponding values for sine square theta are also given in the same table. The value of sine square theta equal to 7a is also not possible. Thus, we can conclude that the powder diffraction pattern of primitive cubic lattice will consider of 6 equally spaced lines following by a gap and then again a set of lines and so on. Now this is a table showing DHKL and sine square theta values of primitive cubic cells. Second, face centered cubic lattice. For this type of lattice, it is found that reflection in face take place only from planes for which HKL values are either all odd or all even. Carrying out the calculation as above, the values of DHKL and sine square theta are given in table 3.7 below. Table 3.7 gives the value of DHKL and sine square theta. Now, thus the lines will be observed at the angle shown in the table. Discuss third, body-centered cubic lattice. For this type of lattice, it is observed that reflections are not observed from the planes for which H plus KL is odd. Carrying out the calculation as before, the values of DHKL and sine square theta are given in table 3.8. Thus, the lines will be observed at the angle shown in the table above. It may be noted that all the will be equally spaced. The diffraction patterns of three types of cubic lattices as explained above may be represented together as follows. Thus, the type of cubic lattice can be determined by observing the X-ray diffraction pattern produced from the sample. The missing lines extend a great help in ascertaining the type of lattice. Knowing the HKL value of the plane from which the reflection takes place, that is corresponding to which a line in the diffraction pattern is obtained, and the corresponding value of sine square theta and hence sine theta, the edge of the cubic unit cell can be calculated using equation 3, which can be written as A is equal to lambda upon 2 sine theta into root h square plus k square plus l square for reflection from any HKL plane, and the corresponding sine theta value, the value of A will always come out to be constant. Next, heading 3.18, crystal structures of NaCl, KCl and CaCl. X-ray diffraction studied of NaCl crystal show that it has face-centered cubic lattice as shown in figure. In fact, this structure consists of two interpenetrating face-centered cubic lattices, one composed entirely of Na positive ions and the other of Cl negative ions. The chlorine lattice is displaced A upon 2 along any edge of the cube. This structure is further supported by the fact that its unit cell contain 4 Na positive and 4 Cl negative ions, that is the 4 NaCl units. Keeping in mind the contributions made by corners 1 upon 8, face centers 1 upon 2, edge centers 1 upon 4 and body centers 1. KCl also has face centered cubic lattice similar to the that of NaCl, in which Na atoms have been replaced by K atoms. CaCl is found to have a body-centered cubic lattice as shown in figure. In fact, it has two simple cubic lattices, one of cesium atom and the other of chlorine atom, which are interlocked together to give pseudo-body-centered lattice. This structure is further supported by the fact that its unit cell contains one cesium positive and one chlorine negative ion, that is one CaCl unit. It is interesting to point out that through NaCl and KCl have similar structure, their diffraction patterns are remarkably different. This is explained on the basis of the fact that X-rays are scattered by the electrons and different atoms or ions contain different number of electrons, hence their scattering strengths are different. Greater the number of electrons, greater is the scattering strength. Moreover, the waves of the X-ray scattered by anions interfere with the waves scattered by the cations, and depending upon orientation of the ions, the reflections may be in phase or out of phase. In case of NaCl, the number of electrons in Na positive ion is less than that of Cl negative ions, and therefore their scattering strengths are different. But in case of KCl, both K positive and Cl negative ions contain the same number of electrons and their scattering strengths are equal. Thus, when out of phase, the scattering strength of Na positive and Cl negative ions do not cancel out completely, whereas in case of K positive and Cl negative ions, the cancellation is complete. The ions in KCl therefore all look very similar, and instead of appearing to be face-centered cubic, the powder diffraction pattern obtained is similar to the primitive cubic unit cell. In fact, the relative position of atoms or ion is in crystal is determined by studying the intensities of the lines obtained in the X-ray powder diffraction photograph. Coordinates of lattice points in different types of cubic crystals. First, for a face-centered cubic, such as that of NaCl, taking the Na positive ions at the corners as the origin so that its coordinates are 0, 0, 0. A. The coordinates of Na positive ions present in the face centers will be 1 upon 2, 1 upon 2, 0, and 0, 1 upon 2, 1 upon 2, or 1 upon 2, 0, 1 upon 2. B. The coordinates of the Cl negative ions present at the edge centers will be 1 by 2, 0, 0, or 0, 1 by 2, 0, or 0, 0, 1 upon 2. C. The coordinates of the Cl negative ion present at the body center will be 1 upon 2, 1 upon 2, 1 upon 2. Second, for simple cubic unit cell, the coordinates of lattice points at the corners are 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Third, for a body centered cubic, lattice points at the corners have the coordinates as in second above, while that of the point at the body centers are 1 upon 2, 1 upon 2, 1 upon 2. For a cubic lattice, distance between any two points with coordinates x1, y1, z1, and x2, y2, z2 can be calculated using the formula d is equal to root over x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square into a, where a is equal to length of edge of the unit cell. The next and the last heading is crystal structure of calcium fluoride or fluorite. In fluorite, each Ca2 positive ion is surrounded by 8 F negative ions, giving a body centered cubic arrangement of F negative ion around Ca2 positive ion. Since there are twice as many F negative ions as Ca2 positive ion, the coordination number of both ions is different, and for Ca2 positive ions are tetrahedrally arranged around each F negative ion. The coordination number are therefore 8 and 4, so this is called an 8-4 arrangement. The fluorite structure is found when the radius ratio is 0.73 or above. An alternative description of the structure is that the Ca2 positive ion form a face-centered cubic arrangement. The Ca2 positive ion are too small to touch each other, so the structure is not close-packed. However, the structure is related to close-packed arrangement since the Ca2 positive ions occupy the same relative position as for a cubic close-packed structure, and the F negative ions occupy all the tetrahedral holes. Here the chapter solid state ends, and this was all about it.